How is it that in a noisy environment, when someone calls you, you can hear that and respond irrespective of all the noises around you? Well, that is because your ears inside are using the concept of the Fourier series. Before going into how this happened, let's first understand what is a Fourier series. Let's start with a simple example. Let's say you have a device that can only take input a certain range of frequencies. Now, when we get a new signal, how can we make sure that the frequencies present in that signal are within the defined possible frequencies? A possible solution could be to break our complex signal into simpler signals representing details about the frequencies in signal. That would make things much easier. If we see a signal, it can be defined using three parameters: amplitude, that is how much energy it has; frequency, which is how fast the signal is moving; and the phase, that is how much displaced it is. And the best way to represent a signal would be either in form of sine or cosine. But why? Because the shape of these waveforms remain the same even on changing the above three mentioned parameters. By doing so, all the signals will have a similar waveform, and we only need to define a way to deal with sine cosine instead of dealing with different waveforms. Plus, we can represent sine cosine in Euler's form, that is exponential form, which is very easy to deal with. Well, that's precisely what the Fourier series does. So, what is a Fourier series? A Fourier series represents a periodic signal as an infinite sum of sine cosine wave components. A periodic signal is just a signal that repeats its pattern at some period. Fourier series can only represent functions that are periodic. However, non-periodic functions can be handled using an extension of the Fourier series called the Fourier transform, which treats non-periodic function as periodic with an infinite period. Mathematically, a waveform can be represented as a naught by 2 plus summation an cos nx plus bn sin nx, where a naught, an, and bn represents the amplitude of a frequency, that is how much energy it has. There is another way to represent a Fourier series, that is exponential complex Fourier series, which we can obtain by representing sine cosines in Euler's form, that is xt equals to summation ck e to the power jk omega naught t, where omega naught is 2 pi by t naught. T naught is the time period of the periodic signal, and ck is 1 by t naught xt e to the power minus jk omega naught t dt. Here you can see how adding sines and cosine waveform we can obtain the original waveform. As shown, we are able to obtain the square waveform and a triangular waveform using just the sine and cosine. Coming back to the expression, I have seen people mugging up this formula, but if you look closely, it is very obvious. So we said we will represent our signal as the sum of exponential coefficient, that is ft equals to c1 e to the power j omega t plus c2 e to the power 2 j omega t, and so on till Cn e to the power j n omega t. Now we just need to find the coefficient c1, c2, and so on. So let's find the ck, a general coefficient. To find it, let's divide both sides by e to the power jk omega t. This will leave us to ft times e to the power minus jk omega t equals to c1 e to the power j 1 minus k omega t plus c2 e to the power j 2 minus k omega t, and so on. Now we will integrate the whole equation for one time period. Why? Because for a complex exponential e to the power jk omega naught t, the area in a single time period is 0, as the value at t equals to 0 and t equals to time period is the same. This will zero out all the terms except the ck term. So now we are left with integration ft e to the power minus jk omega dt equals to t times ck. Taking t other side will leave us ck as 1 by t integration 0 to t f of t e to the power minus jk omega t, which is what a Fourier coefficient was, as you can see in this image. Now that we have understood what Fourier series is, let's see how our ears uses it. Whenever a sound wave reaches our ear, It passes through ear canal and reaches cochlea. Inside cochlea are hair cells. Each hair cell resonates or vibrates for different frequencies. Hence, detecting frequencies present in the signal, or we can say they breaks the signal into its frequency components, which is what essentially a Fourier series does. Now, your name is made up of certain frequencies of sound, and since you are listening your name for a very long time, your ear have given a higher coefficient or weightage to those set of frequencies. Thus, when a sound waveform consisting of your name and noise reaches your ear, you are able to hear your name irrespective of all the noises. We hope you liked the video. If you does, please share it and spread the knowledge. And if you don't like it, do let us know in the comment section why.